Welcome back, everyone. Today we're going to explore one of the most intuitive yet powerful results in calculus, the intermediate value theorem. This theorem captures a simple idea that has profound consequences. Let me start with the real world scenario. Imagine you're driving from Denver to Los Angeles. Denver sits at about 5,280 feet above sea level, while Los Angeles is nearly at sea level. If you drive continuously from Denver to Los Angeles without teleporting or flying, then at some point during your journey, you must pass through an elevation of exactly 1,000 feet. Why? Because you started above 1,000 feet and ended below it, and you traveled continuously. This is exactly the idea behind the intermediate value theorem. So the intermediate value theorem, if f is continuous on a closed interval from a to b, and n is any number between f of a and f of b, where f of a is not equal to f of b, then there exists at least one number c in the open interval from a to b such that f of c is equal to n. So let's break this down. F must be continues on the closed interval from A to B. And there should be no jumps, no breaks, no holes. Then N is between f of A and f of B. Either f of A is smaller than N and N is smaller than f of B, or the other way around. And the conclusion from that is there exists at least one C in this interval from A to B such that f of c is equal to n. Think of it this way. If a continuous function starts at one height and ends at a different height, it must pass through every height in between. Consider the function x cubed minus 2x minus 1 equals to 0. Does this equation have a solution on the interval from 1 to 2? Let's define f of x equals to x cubed minus 2x minus 1 and use the intermediate value theorem. First, f is continuous on 1 to 2 because it is a polynomial and it is continuous everywhere. So first thing you need to state that the domain of f is from negative infinity to positive infinity. Second step, you need to evaluate the function at the endpoints. F of 1 is equal to 1 cubed minus 2 times 1 minus 1, which is equal to negative 2. And f of 2 is equal to 2 cubed minus 2 times 2 minus 1 equals to 3. 3, since f of 1 equals to negative 2, which is smaller than 0, and 0 is smaller than 3, which is f of 2, and f is continuous on interval from 1 to 2, on a closed interval from 1 to 2, then by IVT, or intermediate value theorem, we can tell that there exists at least one c in the interval from 1 to 2 such that f of c equals to 0. There exists a c in 1 to 2 such that f of c equals to n equals to 0. Therefore, the equation x cubed minus 2x minus 1 equals to 0 has at least one solution between 1 and 2. Next example. F of x equals to sine of x plus x over 2. Show that there exists a value c in interval from 0 to pi such that f of c equals to 1. First, let's verify continuity. The domain of sine is from negative infinity to positive infinity. The domain of x over 2 is also from negative infinity to positive infinity. So the domain of our composite function is also from negative infinity to positive infinity. Now, second step, we check the endpoints. F of 0 equals to sine of 0 plus 0 over 2, which gives you 0. F of pi equals to sine of pi plus pi over 2, which will be pi over 2, which is approximately 1.57. Now, since f of 0, which is 0, is less than 1, and 1 is also less than our f of pi, which is approximately 1.57, and also f is continuous on the interval from 0 to pi. So by the theorem, there exists at least one c on the interval from 0 to pi such that f of c is equal to 1. Now notice one thing. The theorem guarantees existence but not uniqueness. There might be multiple values of c where f of c equals to n, and also continuity is crucial. Without it, the theorem fails. For example, if we have f of x equals to x if x is less than 1, and x plus 2 if x is greater than or equal to 1. So here, f of 0 equals to 0, and f of 2 equals to 4. But there is no c where f of c is actually equal to 2 because of the jump at x equals to 1. Now let's look at the last example. Cosine x equals to x cubed. Show that there is a solution. In this case, you will need to find your a and b yourself, or estimate it. So let me show you how the functions look like. So when I graph my cosine, I have 1, -1, pi over 2, pi. So cosine will look something like this. And x cubed looks something like this. So the intersection happens between 0 and pi over 2. So let's make our a equals to 0 and b equals to pi over 2. We don't know exactly where this intersection is happening, but this is where the root is located. So we will define our a and b approximately from 0 to pi over 2. So first thing you need to do, you need to let f of x equal to cosine x minus x cubed. So you need to put everything into one side and define your function. Then, second, the domain of cosine x is all real numbers. The domain of x cubed is also all real numbers. So the domain of your function would be from negative infinity to positive infinity, meaning that all real numbers as well. So we can say that also f of x is continuous on interval from 0 to pi over 2. Third, we evaluate a function at the endpoints. F of 0 equals to cosine 0 minus 0 cubed is going to be 1. F of pi over 2 is going to be cosine pi over 2 minus pi over 2 cubed. That is going to be 0 minus pi cubed over 8, which is going to be negative pi cubed over 8. This is smaller than 0. So conclusion for our n can be a 0, right? Because it is between negative pi cubed over 2 and positive 1. So n can be 0. We can say n equals to 0, right? And 5 from here, we can say that there is number c on the interval from 0 to pi over 2 such that f of c equals to n, or f of c equals to 0 by IPT. And that would be the end of this problem.